Hello and welcome to Iron Beetle, the show where we look under the hood of Beetle, the exciting new database for accounting, and try to learn how you could build a database which is extremely reliable, which is distributed, which is written in Zig, which doesn't allocate memory after startup, and is cool in basically every possible imaginable way. So, if you've been following along, you know that like for the past 2 or 3 weeks, we had giant troubles with actually getting this stream out there live on Twitch because I was like randomly disconnected. So I think I figured out the problem, and the problem is basically Portugal. Apparently, Portugal just bans any kind of streaming transactions, streaming networking traffic, while there are some important football matches online, and apparently that cut my internet connection or something else. But anyway, I don't actually know. But for today's stream, I've actually moved from Portugal to Sweden, using this helpful little tool called VPN. So hopefully we'll be back online from this point on every week on Thursday at 5 p.m. UTC. Okay, so the good thing is that all this networking trouble happened while we were disconnecting how we can use consensus algorithm to overcome networking partitions and whatnot. And today we finally start the new chapter of Irondale. We will be discussing storage engine. So let me reiterate a little bit about like the big picture. So Beetle is a distributed database. It runs 6 replicas which communicate over each other with each other over network, and together they process a sequence of events. Processing is deterministic on each replica, and replicas using consensus algorithm to make sure that every replica processes events in exactly the same order. So from any external observer, it is actually impossible to say that there is like a cluster of 6 replicas. From the exterior, it all looks like a single state machine, which processes events strictly sequentially. What we've discussed is how exactly you like get all those requests from the users, how you replicate them across the clusters, across the cluster replicas to get durability, how you append them to the log, yeah. What we haven't discussed is how exactly Target processes like the actual business logic of double entry accounting. And that's what we're going to start diving in today. But before we get to high level objects like transfers and accounts, we need to discuss the basics. And the basic is like how do you store data on disk? And this is exciting because when I joined Target more than a year ago, I had a pretty good understanding of like this networking and consensus bits, at least in theory, but I had complete lack of understanding how the database actually works under the hood. So I understood that, hey, kind of like you could write like giant SQL query with joins and whatnot, and like through some magic database we'd like somehow come up with data to answer your query, but I had very little idea about like, hey, what's actually happening on disk. I kind of like, well, I know that like the B trees or maybe like LSM trees, and that's it. So what I'm going to talk about for the next couple of episodes would actually be the things I learned here at Target. And the exciting thing here is this is like ridiculously simple as everything in Target. So we actually learn how like you can put the data to disk. Okay, so without further ado, which I try to make deliberately long to make sure that we are actually not getting cut off the internet, and it seems like this is working. Without further ado, let's jump straight into the code. And this time, like, usually you want to start from the beginning or you want to start in the end, but we, in the grand tradition of old Greek and Latin authors, will actually go and start from the middle. We'll like look at the kind of like middle layer of what is stored on disk and start to dig in up and down from there. And what is the middle layer? Well, this is a surprising fact. So I thought that what databases store on disk is like super complicated. Like, you have like this whole like relationship thing and like queries and whatnot, and like obviously there's going to be a lot of like crazy complicated things there. But what I've realized since is that it's actually much simpler. Like, it almost all boils down to a very simple data structure, a sorted set. So you have logically an array of items, and that array of items is sorted, and you binary search inside that array, and that's basically the entire database. So all the power you get from the database is actually comes actually from like combining those sorted arrays in a clever way, and we'll get to that. But first, let's actually look at like how this simple sorted array is implemented. And for that, let's look at the table data structure. Kind of like, okay, this is this is going to be slightly. Okay, yeah, yes. Oh no, actually, there is like block pointer right here. So it will help. Okay, so you want to store on disk a sorted array of items, or at least something which is logically a sorted array of items. So how would you do it? Well, one invariant, like one like large thing here, which will going to become clear a little bit later, is that instead of like just allocating an array of bytes on disk, we will first subdivide our whole disk into so-called blocks of fixed size, which are a little bit like pages in the operating system virtual memory subsystem. So we are going to subdivide disk on blocks, and every data structure which we write to disk will be composed out of those individual blocks. So if you want to store a giant array, which doesn't fit into a single block, you need to have some kind of like an index data structure on top of it. You need to say, okay, my array is too big, so it is stored in 10 different blocks, and here is one like root block which actually stores pointers to all other of the 10 different blocks. And this is what a table. This is what the table is. A table is logically a sorted array of values, but internally it is stored in multiple blocks. So let's start looking here. Okay, block. So block is just an array of block size bytes. The block size, I think, is 1 megabyte. Okay, this is outdated. I think we actually use half a megabyte for a block size, and kind of like this half a megabyte is basically a unit of data transfer between disk and main memory. Okay, so what do I want to say? Okay, so okay, let's try to spell this out a little bit more explicitly, because we already touched on the persistence part a little bit. So in the journal, you know, there was like this write prepare function, which took a prepare and called write sectors to like write prepare to some area on disk. And here we aren't talking about like this block structure at all. Here we just like wrote however many bytes we need for a single prepare. And that is because like logically the data file is actually subdivided. So we have like this data file, and at some point we'll get to looking at every single part of it. But important to say that like first there is like this write ahead log, which is a sequence of prepares, and then there is the so-called grid, a set of blocks essentially. So in the journal, we are talking about like this part of the data file, like the beginning where we store the ring buffer of prepares. Here, and this part is just, hey, write these sectors. Here we've been talking about this grid part, which is subdivided in these blocks. So here our like unit of I/O would be the entire block. Anyway, starting from middle is hard. Okay, so going back to our table, we have this block. Usually, and this is kind of like important, we operate with or not. Okay, I think pointers. Yeah, like the trick is that okay, there's like block. Then there is like block pointer, and block pointer is aligned to sector size so that we can use direct I/O. And oftentimes you actually operate not with block pointers, but with pointers to block pointers. And that's like hugely complicated and something we'll be discussing later. Anyway, okay. So we have like this block pointers, and table stores information inside blocks. Okay, loop, what was it called? Block search. Okay. Yeah. And what I want to look at right now is just like this simple function, data block search. So what happens there? Again, table is a bunch of blocks. Essentially, it's an index block and a bunch of value blocks. And the index block points to value blocks. All value blocks are sorted, and the index block itself stores like pointers to value blocks in sorted order. And like obviously you can like binary search your table by binary searching the index block and then binary searching the value blocks. So here we are going to look at this simple primitive operation, like the inner loop of what happens when you try to do anything with data in Target, and that is like binary searching a single block of sorted values. So, okay, data block, pointer to 0.5 MB of data, which was originally on disk, but is now in memory. How data get from disk to memory? Well, we'll cover this later. But you could conceptually think about it here. This is what's on disk, and we take a key, which we're going to, and our assumption is that this data block stores a sorted array of values. We take a key and we binary search value here. So, okay, let's start with thinking about like the data layout. So this is like the entire data block. How do we get actual slice of values out of here? And this is actually interesting because this is like where type ranger kind of thing happening. So let's take a look here. Blocks are untyped. They are just raw bytes. On the other hand, tables are actually parameterized parameterized at compile time by type of the key and a type of the value. And in this function, data blocks values used, we do this typecasting where we just get an arbitrary array of bytes and then we get an array of values back then. I see that there is a recurring question in Twitch chat about like, hey, why you use Zeek? Why does Zeek make a good language for writing a database in? I think there were a couple of episodes where we already discussed this question. So my kind of like cheeky answer will be, hey, please watch like the 20 hours which we have already recorded. So, but this actually here is like one reason why Zeek is nice language. So you see, like you want this table to be parameterized by the type of things it stores. And in Zeek, writing this generic code, which is parameterized over something, is just much easier. It requires less mental overhead because you don't need like complicated generics. You don't need separate syntax for making your code parameterized over something. You could make do with just functions. So we want to have a table generic. We want to have a reusable table. So we write a function which takes the type of the key, the type of the value, and returns the type of the table. So this is nice. Okay, so let's look how this function is implemented. How we get from raw bytes to the size of values. The core thing is that data block values use things, and this brings us to schema.zeek file, and that one is actually okay. Whoa. I'm slightly surprised that, okay, is it really 2616? Okay, yeah, I was worrying that the font is too much, but I think apparently it is okay. Okay, so schema file defines the layout of stuff on disk. And again, it is important. It is not like the high-level schema which defines what like objects you store in the disk. It is not like data definition language. No. This is a low-level schema describing how like the actual database data structures themselves are implemented. And what we are looking here is at the schema of the data block, which I think we want to start calling values block, and that is like super simple. It is just array of values padded with zeros. Okay, so do we have table data? Okay. Okay, so but again, because blocks are always the same size, but there might actually be different amount of values there, you gotta store the size of the field part of a block somewhere. And here we kind of like make an interesting realization that, okay, where is it happening? Yeah, that before we were talking, okay, how in VSR, like all our messages are essentially single type, and how we design our system so that every message has the same header. Well, surprise, the blocks which we store on disk follow exactly the same pattern. Each block starts with exactly the same data structure as each VSR message. So you could say kind of like that the block is just a kind of VSR message, and it actually is. When we'll get back to protocols for repairing various stuff, you realize that actually we do treat blocks as essentially messages. Okay, so going back here, so we have this table data, which is a schema for table block, for a values block. And we can create one from a pointer to a block. The first thing we do here is that we look at the first 512 bytes of this block and cast those to this header, because it contains all the information in this block. And in particular, like the block header contains these things which are unique to block as VSR messages. So first of all, the address of the block, then the snapshot, which we are going to discuss today, the block type, and metadata bytes. So we have different blocks types. We have different block types. Every block type has an address and a snapshot, but they might have different metadata. And for the data block, this is the metadata. Okay, so let's take a look at what block types we have, because we actually have not very much of them. We have like free set, which we'll be discussing later, client sessions, which we'll be discussing later, manifest, which we'll be discussing later, and finally index and data. And index and data is the subject of, well, at least data, maybe we'll get to index, is the subject of today's episode. So data is this table data thing. Data is what stores the actual sorted array of values. Index is that block which points to a data block. And index plus associated data or value blocks index plus associated value blocks is what makes table. Okay, there is a question in Twitch why the previous videos are 2-3 minutes long, and the answer is at the beginning of this video. Basically, my internet connection from Portugal was very horrible, so I moved to Sweden. And in Sweden, it's actually much easier to record to live stream Twitch. Okay, but actually that's a good question, because I forgot to mention the core thing. The main thing is that although I didn't manage to live stream the previous episodes, they are there on YouTube. So if you want to catch up, then yeah, there is the whole Iron Middle playlist on the Target Middle YouTube channel, and it contains everything which you could just watch. Okay, so going back here. We have like those block types. The index and data is what interests us today. And okay, the metadata for data is essentially those things. The most important thing is that what is the count of values in this block, than what is the maximum amount of values that this table type can store the tree ID, and we kind of like, okay, yeah, we are starting in the middle, but let's dig a little bit up. So, okay, we want to store a sorted array. And we want to store a sorted array in a bunch of fixed size blocks. So we have a data block to store like one segment of an array. And we have then an index block to store a bunch of value blocks. Then you could actually take a bunch of index blocks, and what you will get is that you will get an LSM layer, and an LSM layer will be kind of like implicitly stored in the manifest block. But then what you actually want to do is you want to have like multiple layers, and this is the difference. When we go from the index from a data block to the index to the layer, it's all just like, additive. Like we just take the union of what is there. With layers, it is different because, well, you want your array to be mutable, and mutating array in place kind of like isn't really good because, well, you need to move all values, and like shifting values especially is like horribly inefficient. So what databases do is that they essentially, instead of writing an array in place, they use two arrays, like the old array and then the new array, which contains only the changed elements. And the rule becomes that, hey, you like first look in this like smaller array on the top, and if you get a result, then that's it. And if you don't get a result, you go one way below. So this is layers. And a collection of layers forms a single tree. So a single tree is like logically just a sorted array of things, a sorted set. But physically it contains this pretty elaborate structure of like layers, index blocks, values blocks, whatever. And in the database, you will have multiple trees. So for storing accounts, you will have one tree which stores account objects themselves, sorted by ID. But you also would want, for example, to do lookups in accounts using, well, that's a bad example. Let's say transfer objects. So you have transfer objects, and you like store them in a sorted set keyed by the ID of the transfer. But then you want to look up a particular transfer using, let's say, account ID. Like you want to look up all the transfers which belong to a particular account. How do you do this? Well, you could look up this in the transfers tree, but that requires you to scan all the elements because they are sorted by the ID, not by the account number. But what you could do is that alongside this transfers tree, you could have an index tree, which like basically stores pointers into transfers sorted by account IDs. So kind of like what I'm trying to say is that to model a single logical object, you might need several sorted trees underneath. And we'll discuss how you exactly model a single object of many trees later. But the core point for today is that there are like many trees, and each values block obviously belongs to a particular tree, and this is stored right here. Okay, so unwinding back, what are we even doing here? We want to search a single data block. For that, we go and okay, values used. Okay, I forgot how it works. Block values used bytes. Okay. For that, we need to cast this, the pointer to the whole block to a pointer to a slice of values, and that basically means figuring out how many values are there and casting those things. And an important thing here is that this is also the place where type erasure happens. So you see that this metadata is the same for all tree types. So different trees, like each tree is a sorted set. But a sorted set of what? Every tree can be parameterized, like, okay, there might be like tree of like integers and like tree of strings and like tree of like whatever. So there is like some type information about what kind of value is stored there, what is the size of value, how do you compare those values. And this information is absent on the block level. So here you see that this table data is just a struct. It is not func table data type parameterized by the key type. And all this type information is stored, reified in this metadata. So in particular, like we have this value size. So when we go to block values by just what we do? Well, we cast the beginning of the block to this header. Then we extract metadata from this header. Again, very simple function which basically casts metadata bytes which are typed arrays to metadata. And then we, compute how many bytes do we need? And that is used values from metadata times value size where does value size come from? Okay, I'm confused here. Okay, let's we already have schema here. Okay, this doesn't make sense. So this is block pointer const, and this is already table data. But what is table data? This is where are we? Okay, wait. Okay. Oh. Okay. So I was confused. So data block is the actual block. The data is this schema which describes our layout of our particular kind of data block, and it contains like the size of the value, which at this point is a compile time thing, and it contains the maximum number of values which we store in this particular block. So okay, how was this function called? Search, data block search, use data blocks used. Okay, so we take our schema, which is essentially a comp time thing, this is like computed comp time. And we say, hey, schema, this is the data block. So this is schema, this is the data block. Give me the size of values. Okay, so we cast the data block to the header, then we extract metadata there, and then we get a number of used values there. Okay. And then we multiply the number of used values there by the size, which we know at this point. And that is basically our the subslice of a block which stores the actual value. So this is usually the entire block minus the header in the beginning, minus some padding for unused bytes at the end. Okay, and then we go and take our block and slice it from values of set to value size. And values of set should essentially be and values of set is essentially size of the header. So again, this is like slightly finicky code, because what it describes so kind of like the tricky bit about this code is that usually code describes how things change. It describes algorithm. Here we are looking at the code which describes the state, how things are, just like the physical layout of bytes on disk. So it's a little bit finicky, but still you get the idea. Because it's actually stupidly simple. So we have like this header, then like value 1, value 1, value 2, value 3, and then we have pattern. And that's it. So the very simple code to actually get to the size of values. And I think one interesting thing here is that we have the value size here in metadata as a runtime value, And then we have value size in the schema itself, which is sort of like a comp time value. And I bet we actually should compare those two here. Okay, that's interesting. I think this is missing because we should have assert here metadata size equals wait, it was not this function, it was this function. Okay. I think we should assert here that header metadata value size is equal to schema value size, because yeah, that's missing assert here. Okay. Yeah, anyway, we compute value size, we compute slice of values, we return that slice of values. Let's get back to our table thing, and let's look how the source actually works. And that delegates the function binary search values, which is just a binary search. But I want to discuss, well, maybe a couple of things here. And yeah, this is just binary search with a bunch of assertions. There isn't anything particularly interesting here except this thing. So, kind of like, you know, like usually you want to store like keys and values, and normally you think that there is like the key and it maps to like value, and there's kind of like two separate boxes. But in practice, especially in databases, what you actually want is something different. What you actually want is that you have value, which is big thing. And the key ends up being just some subset of value. So let's look at a specific example. Let's look at the transfer object. So transfer object, this is an external struct, and it like occupies a certain amount of bytes, and this is a value. But the key is the ID of the transfer, and that ID is, I think, is actually timeout. Well, not the timeout, timestamp. Yeah, kind of like that's kind of like the tricky thing in Terminal, that we have like user supplied IDs, which are IDs, but we also have like internal IDs, which are U64 and which are just based on timestamps. So anyway, you see, kind of like you don't want to separate key and value. Key is a subset of value. And this is an assumption which runs pretty deep through the entire Terminal. And you see it here. So although we parameterize this by key type and value type, the core thing we have here is that we have this key from value function which takes a pointer to a value and returns a key. And we binary search in the array of values, not in the array of keys. Actually, let's just okay. I'm going to show some horribly complicated code here, but okay, actually, well, it's okay. It looks simpler than it actually is, but for this transfer object, what the key from value would do is that it would do this. It will take a transfer object and it will return a timestamp masked by the tombstone bits. Because we'll get to tombstones later when we start talking about logically modeling data. Right now we think just about simple sorted array of values. Basically this function here, like this binary search, is kind of like the innermost loop of like TigerBittle. Essentially, like everything else in TigerBittle exists to pass the correct arguments into this thing, which actually would do all the interesting bits here. Do I want to say anything interesting about binary search? Well, no, it's kind of like box standard binary search, except that, well, it optimized. It is optimized quite a bit. One interesting optimization here is that to make binary search efficient, we actually want to omit prefetch instructions so that while we are comparing one item, we actually prefetching the next one there. And you also want to make this code for selecting where you want to go, to the left or to the right in a branch there, so there is like some trick there. But other than that, yeah, it's kind of the box standard binary search. Okay, so this is kind of like middle of things. How we take a single data block and search a key in this single data block. And we search a key, so that is like a subset of value, and we return a pointer to the entire value, if it is there, or null if it isn't found there. Okay. That is how we store. That is how we store. How we find a key in the data block. But remember, a table is a bunch of data blocks. So it is the index block which stores pointers to other data blocks. And the question is, okay, how do we find the data block? If we have like our table, we have our index block. How do we find the relevant data block? Well, let's take a look here. I think this is the function we are interested in. Okay, so we have the index block, and we are going to binary search for an index of something in this index block. And that means we probably need to take a look at the schema for the index block. Okay, so this was data, also known as values block, which is simple, just array of values. And the index block actually isn't much more complicated. Okay, so each index block might refer to data block count max data blocks. For each block referred to by an index block, we store the checksum of this block and the minimum and the maximum keys from that values block, and well, and an address, and then pattern. So again, minimum value, maximum value, address of the block itself, and the checksum. So given this index block, here is how we find data block. We go and look for the slice of keys. Okay, that's actually slightly interesting. Yeah. We go and look for the slice of like, so again, we have array of like minimum values for each data block. We have an array of maximum value for each data block. We go and look for the array which stores maximums. This is parameterized by this thing. Okay, which is again going to be pretty simple. We compute this statically known offset, which is compute. How we just compute it? data. Okay, yeah, which is pretty simple. So we know the maximum number of data blocks which can be referred by the index block. So we kind of like store these arrays just one past another. So we start with the header, and then we have checksums. So checksums is number of blocks times the checksum size, and the checksum size is size of 256. Okay, then we have like k-mean, offset and size, and key max offset and size, and then like addresses. So I'm almost not getting lost here. So essentially, okay, we have this index block. We want to get the slice of key max. This is a comp time known offset into the data blocks, and we just like slice it. And well, this is not entire key max. Again, this is used. So this is only like because the index block is not necessarily full. It like might store at most 1,000 of the data blocks, but maybe at this point it stores only like 100. So this uses this 100, and we should also be getting from the metadata, I think, because key size. Okay, yeah, this is the slice, like the entire space which we allocate for key max, and this is used, and use goes to the metadata, and I think we should look at what is the metadata for table index, and metadata is like key size, true ID, data block count max, and actual data block count. So we go to the metadata, and okay, I'm getting lost here. We go into the metadata, and yeah, in the metadata we have just like this number of data blocks which actually are stored by the current index block. Okay, and we get it. And then we go and binary search in this array, but this time we actually, that's actually interesting, because this like the core of our binary search thing returns an index, and we have two high-level wrappers. One returns the index of matched value, and another returns the actual pointer to the value. And internally, that thing looks for an index, and if we found value with index, its value, otherwise it is null. Okay, so we find the index in the array of key max, which corresponds to the key we are looking for, this key. And this index in the array of key max corresponds to the index of the data block we are looking for. Then we kind of like, so this is like, we found this index. And this index is what might contain this block. But then we additionally double check the k-mean, because again, we only looked for a k-max, and it might be the case that k-max says that, hey, this key might be in this block, but when you actually look at k-mean and realize that it is not there. And that would mean that the key isn't present in this table at all. So we double check against the k-mean and return the data block index. Okay, so how is this used? Okay, this should be called, I think, because it's not index block, it's like data block. It should be called like data block for key. Okay, so how the whole search works? We start with the index block and the key. We look for which values block matches that key, and then we'll be looking for we'll be looking inside that actual data block. So this is jumping slightly ahead of today's lecture to the tree code, but this is kind of like the core search loop here. We look up the index block, we get a data block, and then we will go and read this data block from disk, and then do this search inside that data block. Okay, so do I want to move forward from this point? No, I think it's actually might be a good idea to pause here because we discussed the kind of like low-level basic organization of the data on disk. Okay, let me think for 30 seconds if I want to cover anything else, or whether we should move to summary and conclusion for today. Okay, let's actually get a second look at the schema. Well, no, before we get to the conclusion, let's actually do one more read through the entire schema, because that's important. Okay, so schema for the value block, very simple, just array values. Schema from the index block. Conceptually, it stores for each value block covered by this index block its minimal key, its maximal key, its address, and its checksum. But physically, we store this in a struct of arrays kind of thing, where each array spans at most like data block count maxing. And well, this is actually something I haven't talked about yet, and this is something we'll be probably covering next time. But important thing is that there are comp time parameters for the maximum number of values you can stuff in a values block, and for the maximum number of data blocks you can stuff in an index block. So those things are like necessarily finite. There is only so many values you could have in a single table. How that limit is computed is probably the topic of tomorrow. Okay, so again, every block is just bytes, but every block starts from the header, which is the same VSR header which is used for messages which are sent over the network. There are a handful of block types. Preset client sessions manifest, which is not something we are covering today, and index and data, also known as values, which is something which we used today. Okay. So the index table. The metadata for index block is just the block count, and then this like type-raised information about like what is the size of values, well, what is the size of keys, because table index doesn't store values, it stores only keys, and what is the tree corresponding to this table. This metadata is like runtime and specific to each particular block on disk. This bunch of fields here is comp time. Depending on the type of values you store in a tree, you get certain offsets within the block. And yeah, so let's take a look how we compute all those things. There are just two parameters here, like the size of the key and the maximum number of data blocks we store in a single table. And then we just start meticulously filling out every parameter. So key size is just key size. Block count max is just block count max, the size. Okay, the size is going to be the size of all those things here. and that is the header plus the checksums plus keys twice, because there are min keys and max keys, plus the addresses. Each one of them is like pretty simple. Okay, so checksums, well, how many blocks times what is the checksum? Key size. Similarly, how many blocks times the key size? Address, how many blocks times the address, and the address is U64. So that's simple. Okay. That size. Then the offsets and sizes of each particular array. This is like slightly complicated. Okay, where the checksum starts? Well, where the header ends. How many bytes are for the checksums? Well, we just covered that. Maximum number of data blocks times the checksum size. Okay, so that's checksums. Keymin. Keymin follows right after the checksums. So we take the checksums, we add checksum size, and that's where like the keymin start. Where keymax start, well, where keymin ends, and keymin ends where keymin starts plus the size of the keymin. Okay, key size just key size, data. Okay, similarly, it goes right after keymax. So keymax offset plus keymax size, and whatever is left is padding. Okay, that's simple. Then we can create a table index from block, and again, this should verify metadata, I think. Well, actually, no. I think here. Well, no, we should assert that header metadata value. Well, no, actually, this one doesn't need to verify metadata because we are using metadata to essentially compute things. So this is this one is safe because we take runtime value of a block. There's like runtime value in the block, and we just compute the table index from it. Where we do need to compute stuff is here, where we init at this schema from the compile time values, and then use that to assert runtime blocks. So I think we do miss some assertions here. Okay. So let's try to quickly run this through. Okay, then we have some code to access metadata of the block. Again, so this is the place where we need assertions. Just casting and then extract metadata field. And then we have some code given the schema and given the pointer to the block to access corresponding slices. Okay, so addresses are U64. So we go and slice our block using offset and size. And this is like the entire addresses. This is the addresses of what is actually used, which is the entire addresses, anyway, the entire thing sliced by how many things are actually used, and how many things are actually used is, again, is just in the metadata for this block. The same thing for checksums and the same thing for padding. Okay, simple. Table data, even simpler. Parameter, what says the value, what is the maximum count of values in a single block, compute offsets, compute sizes, compute schema from a pointer to the block, compute metadata, and then accessors for blocks, accessors for values, and well, only values because, well, values block stores only values. It's like super simple. Okay, that's it. I guess I want to maybe emphasize like one more thing is that, well, you see in this metadata, we store value size and 3ID. And in theory, you actually don't need those. In theory, when you access a particular block, you know which table it belongs to, like at comp time. So you know the comp time size or values and whatnot. But the problem with this is that if you erase that information, then when you later look at the disk without having access to the terminal source code, you actually won't know what's there. Like there's going to be like some amount of data there, but you would not be able to interpret it without some extra information, some extra type information which is not present on the hard disk. That's why we actually encode this value size and tree ID redundantly in the disk, so that you could write code which like generically walks over the data file without necessarily knowing the types of all of the trees. Okay, and I think that's basically it for today. So let's answer one more question from the chat, and then let's get back to the summary. Okay, the question is, you like questions about Zig language so much. Well, it's not the point. Like the interesting thing here is like the database. It doesn't really matter which language it is written in, but still the question is like, how nervous are you about the amount of code you might want to rewrite if there is a break and change in the Zig language design? The answer is we are not too nervous for a reason. So in general, yes, Zig is not stable, and you should be thinking a lot about, hey, should I write 1 million lines of code in Zig if it might make a break and change, because Zig does routinely make break and changes, big and small. So you need to have a plan there, and we do have a plan here. So one big thing here is that rewriting the code to update it to a new language version isn't actually hard. You just go and you write it. The hard bit here is updating dependencies. If your project has like 2 dependencies and one dependency is using like Zig 0.9 and another dependency uses Zig 0.10, that is something you cannot do because, well, those 2 are incompatible, and you cannot trivially go to this dependency which uses Zig 0.9 and update the code because, well, it is a dependency. You cannot just update the code. You don't have commit access to that thing. At Terminal, we don't have dependencies. We only depend on the external library. So we don't have that problem. If we need to update the code, we just go and update it. Yes, it takes 2 days of engineering work. Well, it's just 2 days of engineering work a couple of times a year. It's not much. Of course, it would be easier if we didn't have to do that, but well, it's not a big problem. It would have been a big problem if we had dependencies, but well, that's why you don't have dependencies. And the second reason is that, well, we have King on our team. King is a member of Zig's core team. So in general, we do have people who have this expertise of updating the code to new compiler versions, which is not always trivial, but well, we know how to do this. Okay, thank you, by the way, for the questions. I think today this the most questions asked of all time, probably because you didn't have ability to ask the questions that 3 previous weeks where they were not broadcast. But anyway, thank you. Okay, so sum up, LSM tree storage. We started today the new chapter of Iron Beetle, where we store how the data, where we look at how the data are actually stored on disk. We learned 2 things. Well, we learned many things, but some of them are. Well, first, there isn't anything complicated there. We just store sorted sets. That's it. Everything we'll be discussing from now on is essentially how do you represent a sorted set on your SSD. The second thing we learned, without much justification just yet, is that we are thinking in terms of blocks. So if we want to store an array on disk, we don't store just the array. We subdivide disk in fixed size blocks, and then we need to store the array in some number of those fixed size blocks. Okay, and then we actually looked at very specific code to represent a sorted array in this block grid, which is this. Okay, so you want to store array, and you want to stuff array into a number of blocks. First of all, you slice big array into small chunks such that each chunks fit in a block, and you write the chunk into block, and that block is going to be your data block or your value block. But then you need some kind of meta information which says, hey, these are all the blocks which comprise my sorted array. And you write that meta information to the index block. So kind of like in the simple case, you could say that, okay, index block contains just the addresses of all the data blocks. Well, that's not exactly enough because at minimum, you need checksums. Because reminder, target doesn't assume that the disk is inflatable. Target allows for disk failures, and to detect disk failures, you need checksums. So you need addresses and you need checksums. And that is theoretically going to be enough, but it's going to be horribly slow. Because, okay, let's say you have this sorted array on disk, and you want to figure out whether number 92 is a part of this array. Okay, you know all the data blocks. So what you could do is that you could read each of the data blocks, and within each of the data blocks do a binary search and get your answer. But that is slow. Like, you don't want to read you don't want to read every data blocks. So that's why in the index block, you also kind of like include a bit of duplicate information. Besides just addresses and checksums, the index block returns for each data block minimum key and the maximum key. So when you want to find a particular value in this table, what you can do is that first you can binary search in the index block to either confidently say that, hey, this table doesn't contain this value, or to find the index of the data block that contains this value. Then you read the data block and you binary search in this data block. So essentially, yeah, it's a pair of binary searches which gets this thing solved. Okay. Again, extremely happy that we've managed to finally get on air again, and see you again in a week on Thursday at 5 p.m. UTC in Sweden. And thanks for watching, listening, and asking your questions. Goodbye.